Okay, so those were our intramolecular bonds. Now it's time to look at our intermolecular bonds. So these are bonds between atoms. The first example we're going to look at is hydrogen bonds. Now, as the name suggests, hydrogen bonds only form when we have hydrogen. But it would be too simple to say that any bond involving hydrogen is a hydrogen bond. For example, if you remember, in the previous example when we drew water, we had a bond between the oxygen and the hydrogen, where the hydrogen had given its electron into the shared area of the oxygen. Oxygen is bigger, so it takes on a negative charge. Hydrogen has a positive charge, and we had two of those. Well, this bond right here is a polar covalent bond. It is not a hydrogen bond. So where do hydrogen bonds form? Well, like we say, they are intermolecular bonds. So we have to draw a second molecule. So let's go ahead and draw a second water molecule. Here it is. And we have two positive hydrogens and a negative oxygen, and we're going to have a force of attraction between these molecules where the negative oxygen of one molecule is attracted to the positive hydrogen of the second molecule. Okay? Now, why is this kind of bond specific to hydrogen? Well, there's something very unique about hydrogen. What's unique about hydrogen is that it has only one electron in its shell. What that means is when it gives that electron into the shared space with oxygen, there are no other electrons left behind. Now, why is that important? Well, consider this oxygen. As it's approaching the hydrogen and being attracted to that hydrogen because of its positive charge, it's going to be able to get really close to that hydrogen. Nothing is there to repel it. There's simply nothing to push back. If we used any other atom, let's say, for example, we replace the hydrogens with lithium, which we can do because it has the same valency. Lithium has atomic number 3, so 2 electrons in the first shell and 1 electron in the second shell. Well, so lithium would actually be able to replace oxygen over here. So let's go ahead and take away this hydrogen, and we're going to replace that with a lithium. Okay, and if we do that, well, the same kind of thing is going to happen. The lithium is going to give its electron to oxygen a little bit in the shared area. The oxygen will still take on a negative charge. Lithium will still have a positive charge. And so the negative oxygen of this water molecule will still be attracted to lithium, but they cannot form a hydrogen bond because as this oxygen is getting closer and closer, remember, lithium still has 2 electrons in its inner shell. This outer electron has gone to the oxygen shared area, but these 2 electrons here still remain, and their negative charge is enough to push back against this molecule. So that prevents the water molecule from getting really close. The only way for it to be able to get in very close would be if we take away this lithium and go back to what we had previously, which was a hydrogen atom. Okay? Because once the hydrogen gives its electron to the shared area with the oxygen, there are no other electrons left behind to push back against this oxygen. So we form a nice tight bond, which we can call a hydrogen bond. Okay, hydrogen is unique in having only one electron, and so hydrogen bonds require you to have hydrogen. So that was hydrogen bonding. Now, so far we've looked at 3 different types of bonds, 2 intramolecular and 1 of the intermolecular bonds, and we've done that in the order of strength. Ionic bonds are the strongest. They really do hold molecules together quite firmly. Covalent bonds, polar and nonpolar, are slightly weaker but still very strong intramolecular bonds. Hydrogen bonds between molecules are a little bit weaker. Okay, now the hydrogen bonds will be discussed in great detail in the next lesson, which is about water. But now we're going to come to the weakest of all the bonds, van der Waals interactions. Now, one of the interesting things about van der Waals interactions is that they can actually happen between any 2 types of atoms. So it really doesn't matter which atoms we choose to draw for this. So van der Waals interactions were named after the gentleman who best described them, and that his name is van der Waal. And basically we can have 2 atoms, atom A and atom B. Now, atom A is approaching atom B. Okay, if we draw this atom, and we'll just put a couple of electrons in there, and here's another atom. All right, we'll make this a different kind of atom, but again, it doesn't matter which atom we draw, and we'll put 1, 2, 3, 4, 5 electrons in there. Okay, now as atom A is approaching atom B, these electrons are moving around kind of randomly. Now, I know that The quantum physicists and so on are going to get annoyed with me here, but basically for conceptual reasons we can imagine the electrons as orbiting around and occupying one place in time and space. Now these electrons are not evenly moving around, okay? So as these two atoms approach, the electrons are going to be pushed away, okay? And as they're pushed away, that's going to give a slightly positive charge to one of these atoms. Let's say, for example, as A approaches B, the electrons here are pushed away. The bigger atom pushes these electrons away. The same thing's going to happen on this side, but to a lesser extent. And that really does mean that in relation to each other, atom A is going to have a slightly positive charge, atom B is going to have a slightly negative charge. And this London interaction, this attraction between the two, is part of what will eventually lead to being the van der Waals interaction. Okay, so as two atoms are approaching, they're going to reach a point. Now, what is that point where they come together? Well, that would be the point where the outer fields basically overlap. So here again is atom A, and we know the electrons over here have been pushed to this side, meaning this side of the atom is now positive. And we're going to overlap the field a little bit here with atom B. Okay, and atom B has its 5 electrons sort of more evenly spaced around, okay, but in relation to atom A, it's considered a little negative. So there's a force of attraction between the negative and positive here, but there's also a force of repulsion between these two electron orbitals. And so we'll find this distance in between atom A and atom B. It's a very, very weak interaction. As you can see, it's the balancing of two forces. Now, why is this important in biology? Well, van der Waals on their own, being very, very weak intermolecular bonds, aren't really that significant. But when we look at something like a gecko, well, we know that geckos, those lizards, can climb upside down on the ceiling, and they have an incredibly sticky hand that they can use to hold on to things, and hands and feet, or whatever you want to call them. Now, they're actually using van der Waals forces to do that. So a gecko that's able to suspend itself on the ceiling basically is using van der Waals interactions between the many, many, many atoms and compounds and molecules in its hand and whatever surface it's climbing on to be able to grip and hold on. So that's a pretty cool use of van der Waals interactions. Van der Waals interactions can happen between any two molecules. There's always going to be some kind of attraction. Why are they so weak? Well, as the two atoms approach, because of the attraction between the London forces of a positive atom of one and negative atom of another, it's balanced out when the two overlapping fields end up with a repulsion between the electrons. So because it's the balancing of these two forces, one force of attraction, one force of repulsion, it ends up being a net overall very weak attraction. Geckos are able to achieve van der Waals holding on to the ceiling surface because they have many, many, many of those interactions. But we'll see these interactions throughout places. Okay, so these are the 4 bonds. Quick recap. We have 2 intramolecular bonds, ionic and covalent. Ionic is where a metal and a non-metal combine and they transfer electrons, one becoming the one that transfers from is called the cation, the one that receives is called the anion, and it's the attraction between the positive and negative of these two ions that holds the molecule together. Then we have the covalent bonds, which is the sharing of electrons. Remember, covalent, okay, sharing of electrons. If you subtract the valency from the number of electrons it wants to have in its outer shell, you'll get an idea of how many would need to be shared. If the sharing is equal, as in the case of two atoms that are equal size, it will end up in a non-polar covalent. But if one atom is larger, it's going to have a greater pull on those shared electrons and thus take on a negative charge, leaving a positive charge for the smaller atom. We call it a polar covalent molecule. And again, not to confuse that with ions where the electrons have actually been transferred. Next, we talked about our intermolecular bonds. We had hydrogen bonds specific to hydrogen. Why is that? Because hydrogen is the only atom that can give an electron to a shared space and not retain any other negative electrons to repel the approaching negative atom of another molecule. So hydrogen bonds are bonds between molecules that only form between a positive hydrogen of one polar covalent molecule and a negative atom of another molecule. Okay, and then we have van der Waals interactions, which are extremely weak interactions between any two molecules or any two atoms. Okay, and this is where the approaching atoms have an effect on the outer electrons. A larger atom, for example, will push away the electrons of the smaller atom. thus making the smaller atom in relation positive and the larger atom in relation negative, and that positive and negative are attracted up until the point where the orbits overlap, and at that point there's also a negative force pushing back the other way. Because of the balancing of these two forces, van der Waals forces are extremely weak. Okay, so hope you learned a little bit about objective number 2 there. That is the 4 types of bonds. Next, we're going to talk about properties. What properties can we infer from these bonds? And how will that help us to learn a little bit more about some of the molecules and prepare us for our next lesson, which will be a lesson on water. Okay, so for objective number 3, to finish our lesson, we'll need to be able to infer a few properties of molecules based on the kind of bonds they have. So let's look at each type of bond and what kind of properties it brings to the molecule that either contains that bond or has that bond with another molecule. So first of all, let's look at ionic. Well, as the name suggests, ionic bonds are based on ions, and that means we're going to have a positive and a negative. This is really, really important because any molecule that has a positive and a negative is going to interact with other molecules that have some kind of a charge. For example, a positively charged molecule, atom, whatever it is going to be repelled by the positive part of the ionic compound, but it's going to be attracted to the negative part. So we're going to have some interactions. Of course, that's also true of a negatively charged. So pretty much anything with a positive or a negative charge is going to interact with an ionic compound. What about covalent? Well, if it's a non-polar covalent, well then it's really not going to have any of that. A non-polar covalent molecule does not have a positive or a negative. And so it is not going to be attracted or interact in any real way overall with other charges. Okay? What about hydrogen bonds? Well, hydrogen bonds are bonds between molecules. And so we know that when we have anything that has a positive hydrogen because of a polar covalent bond within the molecule and a negative atom in another molecule, there will be a hydrogen bond forming between them. So hydrogen bonds are great ways of joining molecules together that have these kinds of structures. Okay? And van der Waals, we learned, can happen between any 2 types of atoms, molecules, or compounds. Okay? So how does this help us to achieve objective number 3? Well, let's take into consideration, for example, water, which will be the topic of our next lesson. We know that water is a polar covalent molecule, meaning parts of water are positive and parts of water are negative. So why does water, for example, dissolve sodium chloride, salt? You know that if you put salt into water, it dissolves. Well, that's because the positive sodium is attracted to the negative part of the water, and the negative chlorine is attracted to the positive part of water. Thus, water and sodium chloride are going to mix and dissolve very, very well. Okay? If you compare that with something that has, polar covalent or non-polar covalent molecules, they're going to be less attracted. Now let's take sugar, for example. Sugar is full of polar covalent bonds, and because of that, there's going to be pluses and minuses all over this molecule. Okay? Does sugar dissolve in water? Absolutely it does, because again, the positives are going to be attracted to the negative part of water, and the negative is going to be attracted to the positive part of water. So both ionic and polar covalent molecules are dissolvable in water. And we're going to see that in the next lesson when we talk about the structures, properties, and functions of water. Okay, so I hope that helps you a little bit. Please remember structure, property, and function overall. Today we saw how the structures of atoms gives the properties and the kind of bonds they form, and that gives us some of the idea of how they can be used in functions. Okay, our next lesson will be water, and we'll see a tying together. So do please try and watch these lessons in order. I hope you enjoyed today's lesson. See you next time.